10, ideal gas law mainly. So just as an introduction, this is taken from Brown and LeMay's chemistry and also from Zumdahl's. In this particular case, I can't remember which one the slides were based from. As always, they've been heavily edited by myself, the author, and so even though the base slides were from an original set that was put out by the publisher, and I've given credit for those both here. I'll go to the other source in just a moment, but just to be clear, I think there's more stuff on these slides that I put there than was originally there. The format in these particular slides isn't the kind that I really like. However, time constraints are keeping me from going back and redoing these because I'd have to redo the whole slideshow. So anyway, let's talk about the ideal gas law. This is Chapter 10 in Brown and LeMay. Let's go to the next slide and look at our other credit here. So this is Zumdahl. Here they have it as Chapter 5, which that was in the 9th edition. So I'm guessing probably these slides came from Zumdahl or possibly from another textbook that I've used in the past. Anyway, so ideal gas law is the main topic here, which we have already discussed in laboratory. If you happen to do that lab, we have optional labs where you can kind of pick and choose the ones you want to do. If you chose that one, then you're already kind of familiar with this. Let's go to the next slide. Let's go ahead and get the rest of these credits out of the way. So most of the stuff, or not most, but a lot of it, has been done by myself. Probably not as much in this set as others. Let's go to the next slide. So what I want to say at the very beginning is, if I were you, I would spend the vast majority of my time in this chapter studying the ideal gas law. We're going to see that there are two different ways that questions can be posed from it, and I'll mention those a couple of times. But just basically at the very beginning here, let's just go ahead and mention that there are two ways that you can do these. And so I think I'll wait till we get to that. I would spend the majority of my time in this chapter on just this equation you see here, and I don't want to stop now and explain it because we're going to explain it in detail in just a few moments. There's a few other topics. There are a few other topics towards the end. Things like figuring out what a real gas's pressure, volume, or whatever would be, where we have to use a slightly different equation than the ideal gas law. Also, we can adjust the ideal gas law to make it so that we can figure out things like molecular mass and density. And again, we did this in the lab. And then there are a few other topics. So if I were you, again, I wouldn't spend too much time on those other topics because you're just less likely to see problems on exams. But I would spend a little time on them, and I'll point out the things that I really would go through. Other things that maybe you probably never will see again. I tried to actually cull those out, but if I do have one or two slides left in here that you probably will never see again, I'll tell you. So spend some time, I would just say this, spend 2/3 to 3/4 of your time studying the problems for the ideal gas law, because that's going to be about the percentage. On the final, if they take, for example, 3 questions from this chapter, there's probably going to be 2. Maybe all 3 of them would be from just the ideal gas law, either of the 2 forms we're going to discuss. Also, Dalton's law down here at the bottom. Whoops, I accidentally slipped over and clicked it. So my apologies for that. That does happen. Anyway, so I actually didn't quite finish that other slide, but Dalton's law would be another thing that we'll talk about. We'll get to that in just a few minutes. So, all right, so let's start off here. A gas, this is just telling you what it is, which you already knew what it is. It will uniformly fill any container. It's easily compressed, right? I mean, unless it's already been compressed a heck of a lot. So we talk about in 1412 about diesel engines, a little bit about how that the air in the cylinder is compressed greatly. So anyway, and then it mixes completely with other gases. That's because of something called entropy, which we'll introduce and talk about in 1412. And also it exerts pressure. So if you have a gas in a box, even though you really don't think of it that way, it actually exerts a little bit of pressure on the sides of the box. It's a very small amount, but there is nevertheless a pressure there. And also there's a pressure in the air above us. So for example, above us, there's a certain number of miles of atmosphere, and even though excuse me, the gas in any particular small volume of that is very light, there's just so much of it that it actually adds up to about, believe it or not, 14 pounds per square inch, actually almost 15 at sea level. So in other words, here in the southeast Texas around the bay, we're at about 14.7 pounds every square inch that's actually on our tops of our heads and shoulders that we don't notice because we're used to it. Let's go to the next slide. Okay, so here's a little picture. We have a box, we have gas molecules or atoms in there. It could be either one, because it could be either like helium atoms or neon atoms, or it could be like H2 molecules, or it could even be things like H2O in the vapor form or CO2 in vapor form. So, but whatever's in there, this is the way they're typically going to be, where they'll completely fill up whatever volume they're put into. Next slide. All right, and then very briefly, a definition of pressure, which you may or may not have had in physics. Pressure is defined as the force per unit area. So when I just said a moment ago that the air pressure above us, which is referred to as atmospheric pressure, we should probably talk about it in the units that we're going to use. So it's going to be, usually we'll just call it 1 atmosphere. The pressure would be, if you use the units that we've used in the past in the United States, it would be 14.7 pounds per square inch, but we don't use those units much anymore. So in SI units, it would be 1 atmosphere, or you can also do it in pascals, newtons per pascal, newtons times pascals, but we don't usually use that. This one right here, Newton per meter squared is 1 pascal, and 1 atmosphere is 101,325 pascals. So this is one that you'll very rarely see on an exam. If you do see this thing right here on an exam, it's going to be given to you as far as the conversion factor. So you don't have to memorize that. So the ones that you'll need to know would be basically this one right here, this one right here, and this one right here. And you'll notice that these last two that I just underlined are the same. So 1 atmosphere is also the same thing as 760 millimeters of mercury. So when you watch the weather, if you were watching in a centigrade or whatever, a metric country like in Europe or in South America, they would probably give it to you in either millimeters or maybe more likely in centimeters of mercury. In the United States, in the weather reports and even on the gauges, a lot of times they'll still have it in inches of mercury. And notice here that a millimeter of mercury and a torr are the same thing. Now, a torr just stands for Torricelli, who was a guy who did some experimentation in this field. So they named it this unit after him, but they abbreviated it because it's too long to say Torricelli, so they abbreviated it to torr. So what you need to know is that a torr and a millimeter of mercury are the same thing, and that there are 760 of those in 1 atmosphere. So these things here on the bottom are the ones that we're going to be using. So I wouldn't worry too much about this one right here. If you see it again on the test, you'll be given this conversion factor, so you would just convert. All right, and I wouldn't worry too much about this definition here either. Next slide. Okay, so over here on the right-hand side, we've got a picture of a barometer. This is not the way they really are in the weather stations, but they're kind of like along the same principles. What you're doing is you're taking this chamber right here, which is just an evacuated tube. There's nothing in there, a vacuum. And then you put it into a pool of mercury, in this case, here, where you're allowing the atmospheric pressure to push the mercury up until it's the same pressure inside that tube as there is pressing down on the mercury that's in the dish. And if there's 1 atmosphere pushing down here, if this is 1 atmosphere, then this column of mercury here is going to go up by 760 millimeters or 76 centimeters. So if you want to convert that to inches, you can. So what they would do is they would just measure the height of the column from wherever the meniscus is, which would be different for mercury than it is for water, but still all the way down to the level of the liquid here. So you would measure that distance, 76 centimeters. So that's, let's see, 5 times 14, 2 times 14, 28 inches, I guess. Let me think about this. 5, 10, so that's 14, yeah, 20, 29, 30 inches maybe. It doesn't matter. If you were going to do it in inches, it's about, I guess, 29 or 30 or something like that. I never used that unit, that's why I don't know. But we'll use this number right here, so 760 millimeters of mercury, and this is where they're getting that from. All right, so again, pressure, force per unit area. Remember that force is measured in newtons, which is kilogram meters per second squared. So down here it says that the pressure will have units of newtons per meter squared, because the area is in meters squared, right? And newtons per meter squared are pascals. We talked about that on the last slide. And the reason that they use mercury here to do these barometers is because if you use something less dense, mercury is very dense. If you use something like water, you would have to have a column of water that's like 3 stories high in order to measure the atmospheric pressure, which is obviously not something you would want to do if you could possibly avoid it. So you can avoid it by using mercury. So most barometers have mercury in them. Next slide. And here's our same slide here. Here are the units down at the bottom again, so we won't spend much time on this. The ones that we're mainly going to use are atmospheres, and millimeters of mercury or torr. We've already talked about this one. This is kind of like less important to us. And a bar is defined as about 101,000 torr. I think it's 101250, which they were trying, I think, at one point to try to make this the standard unit, but it didn't really go anywhere. So I think that's kind of going to die, and I mean, I hope it does, because everybody is used to atmospheres, and I don't think anybody has any great desire, other than the people that do the standards, to convert over to bar. Anyway, let's go to the next slide. All right, so here again we have another picture of a barometer. It's the same thing we saw before. We have a glass tube inverted into a cup of mercury, and then the atmosphere presses down on the mercury and forces the mercury up into this vacuum chamber inside this glass tube, and you just measure the distance that it goes up, and that gives you the atmospheric pressure. So in Houston it will typically be about 1 atmosphere, and whenever that hot moist air comes off the Gulf, it actually can cause the pressure to go down below that. Because the air is thinner. I mean, it's not thinner, but it's less dense. Whereas when the cold front comes through, which doesn't happen a lot down in this area, so again, we're talking about the area between Houston and College Station. But when they do come through, then they tend to raise the barometric pressure. So if you see a rising barometric pressure, at least in the wintertime, it's a pretty good sign you've got cold weather coming, because the cold air is more dense. Next slide. And then here we have the conversions, which the ones that I would worry about if I were you would just be this one, and this one right here, and this one right here, and I wouldn't worry too much about the other ones. Next slide. The pressure of a gas is measured as 2.5 atmospheres. Represent this in torr and pascals. So to do this in torr, we would multiply 2.5 times 760. So let's go to the next slide. And that would give us our answer in torr. 2.5 times 760 gives us 1.9 times 10 to the third. Next slide. And to do pascals, we have to multiply by just the conversion factor, which is 101,325 pascals per 1 atmosphere. So just multiply this out. You're not likely to see this one. You may see it on the final exam, so you should just be aware of how to do it, but we're not going to work with this one right here very much. So anyway, but you would just multiply by this conversion factor, and again, the conversion factor would be given to you on the exam. Next slide. All right, so let's talk about the gas laws. Next slide. So in ideal gas, we're going to do the calculations, first of all, for what we're going to refer to as an ideal gas, which we'll talk about this a little more later, but we're going to consider this to be a gas where the gas molecules or atoms don't have any volume. So clearly that's impossible. We're going to see that the gas laws that we come up with when we do this, though, are kind of close to what we would get if we used the real gases. So, I mean, it's not unheard of or unfounded to do this. So what we do is we basically assume that the volumes of these particles are zero, and we also assume that the pressures are such that there's no attraction between the different particles, which that's also not true. But if we assume that, it just makes the calculations easier at the beginning. And then it says here we can define these 4 different properties that we can use to do these kinds of calculations or problems. So these are the variables we want to use: pressure, temperature, volume, and number of moles. So N's the number of moles. This is down here. This is the same thing we've been talking about the whole semester. So for example, if you have water, if you had 18 grams of water, then you would divide 18 grams by 18 grams per mole. You would have yourself 1 mole of water. Volume would be measured as, so let's go through the units that we need to use. Pressure needs to be in atmospheres if you're using the ideal gas equation. So this one needs to be in atmospheres, and for certain types of problems, and I'll mention this more later, you have to use these units. The temperature has to be in Kelvin, as it says here. The volume has to be in liters, and the number of moles has to be the number of moles in. So there are some problems where you don't have to do this, and there are some that you do, which I'll explain that more later. Next slide. So to start off, let's look at volume. So we're going to start off by looking at volume, and we're going to see what happens when we compare it with changes in the other 3 things that we mentioned on the previous slide. What I mean by that is, first of all, we'll do it where we'll see what if we have just the volume and the pressure that we're looking at. What if we increase the pressure? What would that do to the volume? Or what if we decrease the pressure? What would that do to the volume? Okay, and then after we do that, we'll do the same thing for temperature and volume, and then we'll do the same thing for the number of moles and volume. Okay, this one that we're going to do first is actually the most difficult. So what is the relationship between pressure and volume? And what they mean by this is the pressure that's on the outside pushing on your container, or, I mean, if you want to think of it in terms of a balloon, if you blow up a balloon, then in this particular case, what we mean by increasing the pressure is we mean squeezing the balloon with your hands to make the volume decrease. So what happens here is a little different from what's going to happen with temperature and the number of moles, because when we increase the pressure, the volume decreases. And let me just say that again for emphasis. If we increase the pressure on the gas, it will cause the volume to go down. In other words, if we make one bigger, the other one gets smaller. You see what I'm saying? So when something is like that, we say they're inversely proportional. So in this case, if we increase the pressure, the volume goes down. So the way that we would write that is right here. We would say that the volume is proportional, where that little thing right there means proportional, or is proportional to, not the pressure, but 1 over the pressure. In other words, if you increase the one, the other one gets smaller. This is the only one that's going to be written this way. So this one is volume is proportional not to the pressure, but to 1 over the pressure. And whenever you have a proportionality like this right here, you can write it as an equation if you put in a constant of proportionality. So we could write this as the volume equals some constant over the pressure. And then we could also rearrange what I'm writing right now, or what I'm trying to write right now with this little marker, as the volume, and this is not supposed to be a y, it's supposed to be a v, times the pressure equals a constant. So in other words, multiply both sides of this equation here, multiply both sides of that equation by p, and you get that the constant is p times v. All right, so with some things, if we plot the volume versus the other thing, the other variable, we get just a nice straight line. In this case, we don't. So let's go to the next slide. Here, this is what we've already said, so I don't think we need to spend any time. There's a shortcut down here at the bottom, which I'll come back to. So let's go to the next slide. All right, so when we plot these two things, we don't get a straight line When we do the other two variables, we will, but for this one, we don't. So over here is where we are right now. On the left-hand side, notice this is what we're getting over here. This is the graph we're getting right here. It's not a straight line, right? So what we're doing here is we're graphing the volume against the pressure, just the pressure. So as the pressure increases, gets bigger this way, what's happening to the volume? Well, the volume's decreasing, right? It starts at the top here at 10 and it decreases all the way down to about 1, right? So that's an inverse relationship, but it's not a straight line, so it's not linear. And so at the very beginning of our class, I gave you a whole sheet that mentioned some different things about mathematics that I said we were going to get to. And this was one of the things that was on there, because if you'll look here, what's happening is that the end of the graph right here is approaching some value. And also here it's approaching some value. Remember we said that when we have something like that, we call it an asymptote. And this whole graph here is in the shape of what we call a hyperbola, because it ends on both sides in an asymptote. So whenever we have behavior like that, if we want it to make a straight line, instead of plotting the volume times the pressure directly, the volume versus the pressure, we can plot the volume versus the inverse of the pressure, 1 over the pressure. And that should give us a straight line if this is pure asymptotic behavior, which we'll see in the next chapter when we talk about the Clausius-Clapeyron equation, that we're going to have some that are not pure asymptotic, so we'll have to do two things to get them into a straight line. But for this one, we don't have to do that. We can just change it to volume versus 1 over the pressure, and we get, voila, straight line. And the reason we try to get it into a straight line is so we can get it in the form of y equals mx plus b, where in this case the y is going to be the volume, and the x is going to be what we've got on the x-axis, which is 1 over the pressure. The b is going to be the y-intercept, which here is 0, and then the m is going to be the slope. So this is going to be the m. And usually when you have a situation like that, you can figure out something that's involved in this relationship that will equal m. Next slide. Okay, let's do our first problem here, but before we do, we said, and I went over it, so now I'm going to have to go through the process of writing it. We said that if we multiplied the pressure times the volume, we get a constant. Okay, so let me just write this out first. All right, so here, notice this kind of problem. Notice the way that this thing is written. We've got a sample that originally has a certain volume of 12.4 liters here. It's at 23 degrees, and that's not going to change, so that's a constant. So we don't have to really worry about this one, so I'm just going to put a parenthesis around it because it doesn't change. And then also we're starting off at this pressure, 0.956 atmospheres. So we have an initial volume here, and we have initial pressure here. And what happens? Okay, so this is one of the kinds of problems that we'll have to do for this chapter. Well, what happens? Well, we're changing one of these things. We're changing the pressure. So whenever we do that, I mean, for example, we could call this one P1 and this one V1 and say this is what we have right here at the beginning of our problem. And then we have another P, which I'm going to write up here to save a little space down there. So this one we could call P2 and V2. And we would have them also equal to a K. And this would be after we make the change. So let me write this K in here. It's so hard to write with this thing. Maybe I'll get better at it eventually. Okay, and it turns out that the K's are the same. So in other words, what we could do is we could just go ahead and write that in here. This is supposed to be an equal sign. And we could write P2, V2, okay, and then we could just actually kind of get rid of the K. They're both equal to K, so that means they're also equal to each other, so we can write P1 V1 equals P2 V2. Now in this problem, this right here would be your V1, and this would be your P1, and this would be your P2. So what we can do is, they're asking us to figure out the V2 here. So this right here, the V2 is what we're trying to figure out in this problem. So to do that, we could rearrange this equation by dividing both sides by P2. So I'll try to write that. The 2's are hard to write. And then we can divide this side by P2. And if we do this side by P2, we get 1. So we get that V2 equals P1 V1 over P2, where all we have to do then is just substitute in the values for this, and this, and this, and that will give us our answer, which I'm going to show you in just a minute, because this is not the kind of problem I can actually, I don't think I can do this in my head. Well, P1 is about 1, so, I mean, if we started off at 12.5 liters, we're increasing the pressure by about, 20%, right? So I'm guessing the volume's going to go down by about 2.4. So look, I'm just going to go out on a limb and take a guess that it's going to drop to 10. I honestly don't remember. But whether it does or not, whether I'm off or whatever, it doesn't matter. But what's happening is that if what we're doing here is we're increasing the pressure from 0.956 to 1.2. So we're increasing the pressure, so that means the volume should go down. All right, so anyway, we'll look at the answer in just a minute. But this is, again, what we call a shortcut problem. And I call it a before-after. So the reason is because you start off with some set of values and you change them. So this is not the kind of a problem where we're going to use the whole ideal gas equation because we don't need to. What we do is we use a shortcut formula, and there are any number of shortcut formulas for different variables, but there's a couple of them that are helpful and useful because they include everything. And so what I do, and what I recommend that you do, is I use one of those complete shortcuts that have P, V, N, and T on both sides. And then you look at the problem and you say, okay, out of the P, V, N, and T, which of those things stays constant? And then you just eliminate that, because if it's on both sides the same, it's going to cancel. And a lot of times that will happen for the end, because a lot of times you'll be doing this in what we're going to call closed systems, where no mass gets in or out. So remember from physics, a closed system is a system where you can't get any transfer of mass. So in those cases, you can get rid of the ends, and then you just have whatever's left over, which I'm going to show you that in a few minutes. All right, so anyway, in this particular case, the only ones that we're going to end up with keeping would be the P2 V2 and the P1 V2, sorry, the P1 V1, because the temperature is also constant, right? Because it says it right here in the problem statement, the temperature stays constant. Let's go to the answer. Sometimes this thing doesn't want to change slides. So here's our shortcut, which is actually like a derivation from the complete shortcut that I'll show you. And then this is what we just did, and it is actually, I was almost on, so it's about 10 liters. It's actually 9.88 liters, and you'd want to get it exact. But the thing is you can use your calculator, and I don't have a calculator here with me anyway, and even if I did, I couldn't use it because I'm trying to hold the computer and talk at the same time. But so it's about 10 liters. So you get the idea here. This is a shortcut problem, and so when we do a shortcut problem, we want the initial conditions and then the final conditions, and they don't necessarily have to be in the units that we talked about a few minutes ago, because what we care about is just the ratios, with the exception of the temperature. And the reason that the temperature matters is because the temperature has to be done in Kelvin, just as it would if we were using the whole ideal gas law. And the reason for that is because if you just use centigrade here, you'll get the wrong answer, because the ratio will be much different. Like if you're going, the temperature doesn't change here anyway, but if it did, like if you went from 23 to 30 degrees centigrade, that's only a change of 7. Whereas if you were doing it in Kelvin, it would be a change from 296 to 303 or whatever. So it would be a much greater proportional change if you're using centigrade, so you can't use centigrade. You have to always convert to Kelvin if you're using the whole ideal gas law, where you have what I call a stationary problem. In other words, you just have one scenario that isn't changing. Next slide. Okay, let's move on to volume and temperature. This one's a little more straightforward. When you cool a balloon off like this is what is happening in these pictures, then the volume also decreases. So if you decrease the temperature, you decrease the volume. Next slide. So what happened to the gas in the balloon? It got smaller in volume because the temp went down. Next slide. So we can do another little relationship here that we like the one that we did for pressure and volume, but this time there's a direct proportionality, so we don't have to write that something is proportional to 1 over something else. We can just write that the volume is actually proportional to the temperature. Let's look at this for just a moment. So that means if the temperature goes up, the volume goes up also. So that, again, that thing right there stands for is proportional to, and whenever you have a proportionality like this thing right here, you can rewrite it as an equation if you put in a constant of proportionality, where this would be a slightly, or well, it would actually be a completely different constant from what we talked about when we were talking about the pressure and the volume. So again, we could do the same thing we did before, but I'm not going to take like all the time it would take to rewrite all of this. But what we can do is we can say that if we have a set of initial circumstances and then we had a set of final circumstances, then we could call the initial V1 and T1 and the final V2 and T2. And we can say, like, if we rearrange this thing right here to get K by itself here, this K by itself on one side, then we would have K equals V over T, right? So we could also say the same thing for V2 and T2, that it also equals K, where the K in that case would be the same as the T1 and the V1K. So since the V1 over T1 equals the same K that the V2 over T2 equals, then that means the V1 over T1 equals the V2 over T2. So this is your second shortcut. Again, we're going to have another one later that will encompass all of these. So here's the second one. If you just want to use it by yourself, you can. Sorry, by itself. The only caveat here is that you have to be sure and remember that the temperature has to be absolute temperature, and that's for the reason that we mentioned a few minutes ago. So if we had a problem where we were given 3 of these things like this, we were given this, we're given this, and we're given this, then we can figure out what this is, right? By just rearranging this equation here to get T2. Oh man, this thing. To get T2 by itself. Next slide. And in this case, we don't have to do any manipulations to get our straight line, because if we just plot the volume versus the absolute temperature, we get a straight line and we don't have to do anything to it. We don't have to take any like inverses or anything. So the difference between these two is just that this one over here is done in degrees centigrade and this one is done in degrees Kelvin, but it doesn't really matter. They both give a straight line. Next slide. Here's a picture of what we're doing. So here, starting off, if we are at 200 Kelvin and we heat it up to 400 Kelvin, then we might imagine that the volume should double, because the ratio of 400 to 200 is 2, right? So we would expect that 0.5 liters would become 1, and that's what does happen. So this is a linear relationship where if you double the temperature, and this is going to be the absolute temperature, then you'll also double the volume. So let's go to the next slide. So an example is, suppose a balloon containing 1.3 liters of air at 24.7. What I would do if I were you is immediately convert that by adding plus 273, just so you don't forget it and do the whole problem and then realize you screwed up and have to do it all over again. So add 273 to that to get it to K, and also to that right off the bat. That's what I would do. This is going to be our V1 here, right? So, or V initial, whichever one you prefer. This is going to be T1, and this is going to be T2. So T2. Okay, so V1 over T1 equals V2 over T2, and we know what V1 and T1 are, we know what T2 is, but we don't know what V2 is. So what we can do is just write out our little shortcut formula, and the units are going to be fine as long as we convert centigrade to Kelvin, and then just solve for the one that we don't know, which is V2. Next slide. Next slide. Finally. So when you do what I just said, you're just adding 273 to both of these temps. Use V1 over T1 equals VF over VI over TI equals VF over TF. Solve for VF or V2, and you get that V2 is 0.849 liters. And this is just basically simple mathematics. So again, this is another before after, which I'll just write as BA, before after. And so that means that you don't have to use any particular units for this. So if your volume had been in milliliters rather than liters, then you could just leave it that way. The only thing you have to be sure you watch out for is the temp. It has to be absolute temp. Next slide. This thing really doesn't want to change. Okay, and then let's look at the relationship between the volume and the number of moles. Right then, so for volume and number of moles, we have the same type of a relationship as we just had with volume and temperature. In other words, if you increase the number of moles in the balloon is going to get larger. So it's just like with temperature, and the relationship here is just like if you had a balloon and you blow it up bigger, then when you blow it up, that means you're putting more air into it, and that's just the same thing as increasing the number of moles, and that makes it bigger. And we have the same type of a relationship here as we did with the temperature and the volume. We have a proportionality where the more N increases, then the more V increases, so it's a direct proportionality. So we could rewrite this as V equals Kn, where we substituted the equals K for the proportional sign. And we could also rearrange this, and we could keep K on one side, and we could say that K equals V over N. That could be V1 over N1, or it could be V2 over N2. So what we can actually do is the same thing we did previously. We can write this as V initial over N initial equals V final over N final. So this is the shortcut, and for these, the number of moles has to basically be in the number of moles. That's really the only unit we have for that one, but V can either be in milliliters or whatever. Next slide. And here's a picture of this. So on the left, we have a lower volume. On the right, we've blown more air in or put more air into it. So the volume has increased. Everything else staying the same. Next slide. So here's our sample problem. If we have 2.4 moles of argon, just looking over this real quickly, I can see this is a before-after problem. So I'm going to call this N1. And the 2.1 moles is what we're going to end up with at the end. So let's call this one N2. And our initial volume is going to be V1. That's going to be 89 liters. And V2 is what we're probably going to be looking for. And yes, it is, because here it is right here. So this is going to be V2, and this is the one that we don't know. So what we'll do is we'll use V1 over N1 equals V2 over N2. Next slide. Which is our shortcut here, and substitute everything that we know in and solve for V2. So this is what we're trying to find. The other values were all given in this problem statement. So when we solve this equation, we get that V2 equals 76.3 liters. Okay, let's go on to the next slide because we're getting a little bit behind here. So here's a summary. These names, Boyles, Charles, and Avogadro's, you really don't need to know those. What we care about is the relationships. So here we have three different shortcuts. PI-VI equals PF-VF, VI over TI equals VF over TF, and VI over NI equals VF over NF, which at some point what we'll do is we'll combine these. Next slide. All right, so and that isn't what I was just referring to, but if we do combine these in a different way, where we have these three different Ks, right, but there's a way that we could actually combine all three of those Ks because they are Ks, they're just numbers. So if we combine all three of those, we get something that we could call K, but in this case we're going to call it a different letter. We're going to call it R, but it is still just a constant. It's just that they gave it a special name and they call it the gas constant or the universal gas constant. and it has a bunch of different values depending on what kind of a system you're looking at. But the ones that we're going to focus on in general chemistry would be, one of them is 8.314, and that's in joules per mole K. And then there's another form that you would use in different problems, which is 0.082, and that's liter atmospheres per mole K. We'll use both of those. So one of the challenges for problems in this class and in 1412, if you take it, would be to remember not only how to do the problems, but also which form of R to use, although you can usually figure it out by going by the units. So anyway, if we did what I just said and combined all three of these, so we had like P1V1 equals P2V2, but we originally wrote that as PV equals K, and then we wrote V over N equals K, and we wrote V over T is K. So if we took the K and changed it and combined them into one, call it R, and then wrote everything that we just wrote as one equation where everything's in it, this is what we would get right here. This is called the ideal gas equation. PV equals nRT. So whenever you get a problem, and how many variables do you see here? Okay, how many variables do you see? Well, how many things are there total? 5, right? PV, nRT. But one of them is not a variable. Which one? Well, it's the R, right? It's not a variable. It stays the same all the time. So how many variables do we have? 4. So typically what they would do in what I call a stationary problem, where there's not anything changing, would be to give you 3 of those 4 things and ask you to figure out the 4th one. And again, that's the thing that you're going to see most often. When you're doing that kind of a problem, you have to be sure you use the right units, otherwise you get the wrong answer. So again, for pressure, you'd want to use atmospheres, for volume, liters, for N, number of moles, and for T, Kelvin temperature, absolute temperature. And for R, it'll depend on the problem. You can use 0.082 or the 8.314. Next slide. So here it is again, PV equals nRT. Here are the 2 values for the R. So some of the problems we'll do today, we'll use this one. Some other problems we'll use in different chapters, we'll use this one. We'll get to that, and you'll start to understand why we're using different values. But they're both the same, okay? They're just in different units. And when we do this here for temperature here, whenever we talk about these things being done at standard temperature and pressure, or STP, that means that we are at a pressure of 1 atmosphere and a temperature of 0 centigrade. So notice this is tricky, because when we did thermodynamics, we called standard temperature what? Was it 0? No, it was what? 25 degrees centigrade, right, which is 298 Kelvin. So it's different. So you have to really watch that, especially on the final. You just have to memorize this, that for the gas chapter, if you have a problem that deals with ideal gases and you're told that you're at standard temperature, you want to use 273, not 298. For both chapters, the pressure at standard pressure would be 1 atmosphere. Let's go to the next slide. I'm trying to get caught up. So here's an example of that one. All right, so look at this. Here are your factors you want to be looking for. First of all, we're given a temp here and a volume, and we're also given a pressure. Well, that's 3 things already, right? Now, they could change 2 of those, and so you would have a possibility that this could be a before-after, except that nothing in here is changing. So you just go by what they give you. So notice I wrote here that this is a stationary problem. Nothing's changing, so it's stationary. When you have a problem like that, you have to make sure the units are right, and then just use PV equals nRT. So what is N? What is N? Well, we don't know that, right? That's what we're trying to figure out. What is T? Here it is. It's 23 degrees centigrade, but do we want to leave it like that? No. We have to add what? 273, and that becomes 296 Kelvin. And then what's the volume? 25 liters. That's okay, right? And the pressure is 3.18, and that's an atmosphere, so that's okay. So how would you find N? Well, you use the ideal gas law. So PV equals nRT. If you rearrange that, you can get N by itself, which we'll see on the next slide, and it would equal PV over RT. And which value would you use for R? Well, it turns out you'd have to play around with it, but it turns out that it's going to be the 0.082 liter atmospheres per mole K. Let's go to the next slide. So if you rearrange the ideal gas law from PV equals nRT here up at the top, rearrange it to get that so that you've got N by itself. Why are we trying to do that? Because that's what we're trying to figure out is N. So N is PV over RT, and then all you have to do is substitute in the values for PV, R, and T, which we refer to as just plug and chug. In other words, just put the values in and figure out the answer. It's not difficult. Again, be sure here that you remember that that can't go in as 23, right? And so just do the math here, and it's 3.27 moles. Next slide. What is the pressure in a 304-liter tank that contains 5.67 kilograms of helium at 25 degrees centigrade? Is this a before-after problem? Well, look at it for just a moment. Do you see any before-after type situations here? Is anything changing? No. So it's probably a stationary problem. Let's see if we have at least three things given. So here's the volume. This can be converted into the number of moles, and this is the temperature, which we have to remember to add 273, so the temp will be actually 298 Kelvin. So if we have three things that are given to us, we can figure out what the fourth one is, right? So we'll use 270. This is going to be 298 here. This is going to stay exactly the way it is. And this one we're going to have to do some work on. First of all, notice that this is given in kilograms, so that has to be changed from 5.67 kilograms to 5,670 grams. And then what do we have to divide that by to get the number of moles? And this is helium, so what's the atomic mass of helium? It's 4, right? So we divide 5,670 by 4 to get the number of moles of helium, and that gives us 3 of the 4 things. What are we trying to find here? The pressure. So if you start with PV equals nRT, you rearrange it and you get P equals nRT over V. And let's go to the next slide. I'm having to hit these things like 5 times to get them to change. So start with PV equals nRT and rearrange, and you get P, which is what we're trying to find here, equals nRT over V, and then just substitute in for all of these 4 things right here, and you'll get your answer. To get the N here, we have to divide 5,670 by 4, and we get 1,400, should be a comma there, 1,417.5 moles, okay, times the R value. And if you'll notice, the reason that one of the ways you can tell we should use 0.082 here is because the units all cancel except for this one right here. So the liters cancel, the moles and the K's cancel. So if that happens, then that's a good sign that we're using the right one in 0.082, not the 8.314 one, and the answer is 114 atmospheres. Let's go to the next slide. Oops, doggone it. Okay, I accidentally slipped over to the second slide because I was clicking away at it trying to get it to go. So actually, I can't go backwards, so I don't even know what was on that previous slide, but let's just go ahead and assume it wasn't too important. So at what temperature in degrees centigrade does 121 milliliters of CO2 originally at 27 degrees centigrade and 1.05 atmosphere occupy a volume of 293 milliliters at a pressure of 1.4 atmospheres? Okay, let's stop and take a look at this. So yeah, we have a change here, right? Because we started off at 121 milliliters of CO2 and ended up with 293, so the volume got bigger. And we had originally a temperature of 27 degrees, and they want to know what the temperature would be after we do all of this stuff. So this one right here is going to be the T2. The 27 degrees is going to be what? The 27 degrees is going to be T1, but we have to remember to add that to 273, so it would be 300 Kelvin. And then the pressure is given here as 1.4 atmospheres, and it doesn't look. No, it does change. Okay, so P1 is going to be 1.05 atmospheres, and P2 is going to be 1.4. All right, now this one is a little different, right? Because how many different things are changing here? All 3 of them are, right? So what we can do here is we can use another shortcut, and this one is really the best one to remember. It's P1V1, which I'm using a ton of time to have to write these up, but P1V1 over T1, so I'm only writing the things that I think are really important, equals P2, and so maybe I won't even try to write this out, but it's going to equal, okay, I'll try. So P2, the 2's are really hard to make, V2 over, guess what, T2. Now this is kind of like a general shortcut that allows you to do most of the problems as long as you have a closed system, because if there's only one thing we left out, right, and that's the n. So if you wanted to put that one in, you'd have yourself P1V1 over N1T1 equals P2V2 over N2T2, and that one covers everything. So I mean, if you want to always start with the one I just said, you can, and you don't have to write it down right now because it's on one of the slides we're getting to. So either this one, if you want to use this one to start with, as long as the number of moles doesn't change, or that one, the one that I said a minute ago with the n in it. They're good ones to start with, and then what you can do is just check the problem statement and see which things stay constant. In this case, nothing does, so we're going to have to substitute in everything except the thing we're supposed to find, which is T2, which is this thing right here. So this is the thing we're trying to find. Everything else, though, we know. So, for example, here, so originally we had a temperature of 300 Kelvin, so that's T1. And this right here is going to be P1, and I'm not sure which one of these volumes, the way they have this silly thing written. So let me read it again. At what temperature does 121 milliliters originally, okay, so I'm pretty sure that this is V1, and this one is V2. So anyway, everything is given to us except T2, if I'm reading this right. So notice here that they give us the volume in milliliters, but that's okay because this is not the ideal gas law. This is a shortcut, so we can use it the way it is. All we care about in that case is the ratio. So what we'll do is we'll substitute in the values that I just mentioned for everything except the one thing that we don't know, which is this thing right here, and solve for that. Next slide. I think this thing is punishing me, but I don't know what I did wrong to it. Boy, it just won't switch. So anyway, here's our shortcut. P1V1 over T1 equals P2V2 over T2. You can look at this and you can think to yourself, wow, this is going to take some time to rearrange this bad boy because it's so messed up. To try to get T2 by itself is going to require some effort. But if you put the effort in, this is what you should get. So you should get P2 V2 T1 over P1 V1. And then once you finally do that, you've got yourself the equation that you need there to solve for T2. And then all you have to do is substitute in the values here. So V2 was this one. So 0.29 liters was the V2. And then the 0.121 liters was the V1. So notice here that I did convert those to liters, but you don't have to do that. And so anyway, when we solve this for T2, you get about 970 Kelvin. But they didn't want it in Kelvin. So here you're getting the right answer, but it's in the wrong units. So they want this to be in centigrade. So in order to get it from Kelvin to centigrade, you have to subtract 273 kelvins, and you get 696 approximately degrees centigrade. So, I mean, really, if there's one problem in this whole chapter that I would really look at, it would be this one. Because it's an ideal gas law problem and uses like the main shortcut. So like what I'm talking about is the shortcut right here is like one that if you can just remember this one, basically it will allow you to do most of the before-after problems. So just to go back to what I was saying a minute ago, and I won't dwell on it, but if you have a problem and you start with this general shortcut, we could just call this a general shortcut, right? If you start with this, and then if you look at the problem statement and you notice that they tell you that, for example, they tell you the pressure is constant, then you can just remove the p's. Because if they're constant, they just cancel, right? So that just leaves you with V1 over T1 equals V2 over T2. Next slide. Gosh. Okay, what if we took everything at standard temperature and pressure? So what does that mean? Well, it means if we took a gas, which we're assuming to be an ideal gas, remember that just basically means that the gas particles don't attract each other, they don't have any volume. Okay, so, I mean, is there a real gas like that? No. However, we're going to see that some real gases actually behave very close to that. All right, so if you had a gas, which is an ideal gas or one that behaved very much like it, then if you took it at 1 atmosphere and at 273 Kelvin, and then if you took 1 mole of it, then if you rearrange the ideal gas law that we talked about a minute ago to get V by itself, and if you use the 0.082 thing for R, you would get this value right here. And I very strongly recommend you try that on your own, because it's a good exercise to do to convince yourself that this is what would happen. So we just start with the ideal gas law, rearrange it to get V by itself, and then substitute everything as if you were at STP, which is standard temperature and pressure. In other words, 1 atmosphere and standard temperature is 273 Kelvin, and just see what you get for your volume. And if you do, you should get this thing which is called the standard molar volume, because it's the volume of 1 mole of gas at standard conditions, standard temperature and standard pressure. Standard temperature is 273 or 0 degrees centigrade. So 22.4, you might memorize that value, because I don't think, I'm not sure, but I don't think that one's on your formula sheet. And if it is, I think it's because somebody was generous. So remember this, memorize it. 22.4 liters is the standard molar volume. If you forget it, you can always refigure it out, but it's just that you don't have time to do that on a test most of the time. So this is just an interesting exercise. But so what can we do with this? Well, one thing, among other things, we can try to look at the volume of 1 mole of other gases at STP, like hydrogen, H2 or He, and see how close are they to 22.42. So let's look. Next slide. Next slide. Okay, so we've already kind of talked about this, so next slide. All right, so here are some real gas volumes at 1 mole at STP. So notice here NH3, well, that's a pretty big molecule, but it's pretty close, right? 22.42 versus 22.40. Not bad, especially when you consider that NH3 is very polar, and that's because it has that lone pair, so it can make hydrogen bonds. And yet still, so that means, what does that mean? It means there's a lot of attractions between the NH3s, and yet still it's pretty close. Remember, one of our assumptions for an ideal gas is that there's no attractions. Argon, let's see, helium here is the one that's really close. So we're looking for 22.42 actually, although we're going to abbreviate that or round that off to 22.4. But it's actually 22, well, down here they're saying 22.414. On the previous slide, they were saying 22.42. So anyway, either way, this one right here is very close. And that's because helium is H2 with a duet, so it's not going to have any kind of like attractions to anything else, and that makes it a little bit more ideal. H2 is also very close, 22.43, and so we don't want to spend a lot of time on this, but just notice this. So if we had a perfect ideal gas, no attractions, no volumes, we would get 22.414, and this is what some real gases actually do look like, and they're pretty close. All right, so go to the next slide, please. Okay, so a sample of oxygen gas, remember that's going to be O2, not O, has a volume of 2.5 liters at STP. That means 273 Kelvin and 1 atmosphere. How many grams? So if we know V, and if we know T, and if we know P, what can we figure out? We can figure out N. So we can figure out N, and then they're asking for the grams. How would we figure out the grams from the N? Well, you have to multiply the number of moles times the grams per mole, which in this case it's a molecule. It's not an atom because it's O2. So even though it's two O's, it still counts as a molecule. So we multiply the number of moles of O2 times its molecular mass, which is going to be what? So if you have a chart, you might just look up O if you don't remember. It's 16. So just O by itself is 16 grams per mole, but for O2 it would be what? 2 times 16, right, which is 32. All right, next slide. So this is how you would figure this out. Next slide. When you do this calculation, and for the sake of time, I'm already at an hour. I've got to wrap this up. We've still got a lot to do. But that's okay. So we rearrange PV equals nRT. We get N equals PV over RT and just substitute N here, and we get that N is 0.112 moles of O2, where the 1 here came from STP, and this came here, 273K came from STP, and this is R, and the 2.5 liters was given to us in the problem statement. So just solve for N, and you get 0.112. You should do this on your own, and then multiply it by the molecular mass for O2, which is 32, as we said, and the answer is 3.57 grams. That's all you have to do. So this is not difficult. Next slide. All right, now we've already also done this, as I mentioned previously. We did this in one of the labs. If you didn't happen to do that lab, what we did was we started off with the ideal gas law, and we made one substitution. We substituted for N by how we find N, which was what? How do we find the number of moles? We take how much we have divided by how much 1 mole weighed. So you would either divide the grams that you have by the atomic mass, if it's an atom, or by the molecular mass. I'll just write AM. So that stands for atomic mass, so it's how much you have divided by how much 1 mole weighs. Or it could either be G grams per the atomic mass or per the molecular mass, depending on if you're dealing with an atom or a molecule. All we do is we just substitute that thing right there in for N, and then do some rearranging. And when we do that, we get, we start off, first of all, we get this, and then we get this. And then if we realize that this, so what they're doing is they're writing this G here as a lowercase m, as mass, same thing, this one right here. So anyway, but when you recognize that the mass divided by the volume, so when you divide that into this, you get the density. Remember, density is just the mass divided by the volume. So that allows us to substitute in density into the ideal gas equation. So in other words, what we have done here is we've replaced the N with lowercase m over capital M. They're calling this capital M here, so that's the molecular mass. Same thing. And so what we can do is we can rewrite this so that we have a way to figure out what the density is instead of the things that we were figuring out before, and also the molecular mass or the atomic mass. So they're just writing that as this capital M. So this capital M could either be the atomic mass or the molecular mass. So what I did down here at the bottom is I put them in where this is the way you would figure out what the molecular mass is, and this is the way you would figure out what the density is. So when you have a problem, you just have to substitute in the things that you are given in the problem statement, and then figure out the thing that you're supposed to figure out. Like, for example, here, for this one here at the bottom, if they're asking you to find the density, you need the molar mass, the pressure, and the temperature, and you can figure out what it is. So again, we did this in one of the labs. Let's go to the next slide. So what is the density of F2 at STP? So we would have to look at the chart, and if we did that, we would see that the mass of F is 19, but this is F2, so its mass would be 38 grams per mole. And what does STP mean? It means standard temperature and pressure, which, what's standard temperature? 273, standard pressure is 1 atmosphere. So we can use that formula that we just saw on the previous slide. Let's go to the next slide, which I have also rewritten here at the bottom. And so actually this looks like the slide we just did. Let's go to the next slide. So what is the density? Next slide. This is one of these slides that has more than one part. So next slide. Next slide. Okay, so the density is going to be the molar mass times the pressure divided by RT, where we're going to use the 0.082 form of the R. So you don't have to write all of this. I mean, sometimes they go overboard here. Just write 0.082, unless you just want to do it the long way. 19 is the atomic mass of F, but we have to multiply it by 2 because it's F2. The pressure is 1 atmosphere and standard temperature is 273 Kelvin. So notice here, check it out, we're figuring out the density of F2 in this particular system. Next slide. So the density is the kind of thing that you could see. I mean, this is actually the kind of thing that I might ask on my exam, and you could also see it on the final. So for that previous problem, be sure you look that over and understand how to do it. All right, so now let's go to gases and stoichiometry. All this means is that we're going to go back to our old friend stoichiometry, or maybe for some of you it's our old enemy. Remember, the stoichiometry is just where you're comparing the coefficients and the reactants and products of the reactants and other reactants, right? So we just want to include that now in one problem, and then we'll go on to something else. So next slide. So let's do this one, and we're just going to set it up because I'm totally out of time. And we still actually do have a long way to go. So I'm going to just set this up for you and let you look at it or pause the video when we get to the solution. By the way, this was something that I did my very first year of teaching. I was actually teaching in College Station, and the next slide is a real mess. I'm not proud of it at all, because it's got arrows all over the place, but it was done in haste. So you just have to have mercy on me for this, but that's what I came up with. But anyway, let's set it up. We have this equation. So this is the stoichiometry, and the thing that we really care about here very quickly is that 2 right there and this 3 right here. So they're telling us how many grams we have of this sodium azide stuff. So just look it up. N is 14, right? 14 grams per mole. Sodium is 23. 3 times 14 plus 23, I think that's 65. And we're given 45. So divide how much you have by how much 1 mole weighs. So 45 divided by 65 is about just roughly 2/3 of a mole. So, but we don't care about how many moles. We care about how many moles we have of this, but mainly because we just want to figure out how many moles we have of the gas, because this thing over here isn't a gas. So we don't care about it except just to help us to figure out how many moles we have of the gas. So what you would have to do is divide 45 by 65, and that would give you the number of moles of the NaN3, which, I mean, not that you're ever going to need to know this probably, but it's called sodium azide. Okay, so whatever number of moles you get there, you want to multiply it by 3 over 2. This number over this number, because for every 2 moles of the NaN3 that you have, you're going to make yourself 3 moles of the N2. So just multiply, like, I mean, this is not the way it would be if you did the calculation, but just say, for example, you wound up with 2 moles of NaN3. Well, how many moles would you have of N2? You'd have 3, right? So anyway, that's going to give you your N, and everything else after that just kind of falls into place. That's actually the hard part of the problem, because you already know the pressure here and you know the temperature. So that's 3 things right there. And then you just find out the volume. So what equation would you use? Just use the ideal gas law, right? PV equals nRT, where you know everything except what? V. And that's, how about that? That's what they're asking us to figure out. So just be sure your units are right. So you'll have to add your 273 here. That's going to become 303. So this is going to become 303 Kelvin, and everything else. The only thing we need to do is divide the 45 here by the 65. So let's go to the next slide. Oh, it actually changed on the first click. So divide 45 by 65. I told you this was a mess. Divide 45 by 65, and whatever you get for that number, which I didn't take the time to write it out here. Again, I'm guessing it's about 2/3 or like 0.66. So, and then you multiply it by 3 moles of N2 for every 2 moles of NaN3. So that's just your stoichiometry. So this is where your stoichiometry comes into play here. And you'll be glad to hear that that's the last time we'll mention that this chapter. So when you do that, you get your N is 1.04 moles of N2. And everything else we already basically know, or we can find very easily. So 273 plus 30 is 303 Kelvin. So here's our T. And we're going to use 0.082, and you can just use 0.082 again. You have to put all of that other in there. And then the pressure was given as 1, let's see, what was the pressure? I don't have it written down. 1.15 here. And then just solve for V. So this just came from PV equals nRT. So just rearrange it to get V by itself and solve, and you get 22.5 liters. And there's your answer. So this one just has what additional step? The additional step here is that you had to use stoichiometry to figure out the number of moles for your gas. Next slide. All right, so Dalton's law, because our time is almost up, because these videos, if you get them too long, then it absolutely takes forever to upload, and they take up huge amounts of space, and they take you guys forever to watch, and most of you just don't have that much time to sit down for an hour and a half and watch a video. So I'm going to try to wrap this up as quickly as I can, but we still have a few things to talk about. Dalton's law is basically just saying that if you have a gas that is a mixture of more than one gas, like let's just say you've got a balloon and you somehow managed to put hydrogen gas in it and helium gas and nitrogen gas and maybe oxygen gas. You wouldn't want to do that, but if you did, then the total pressure of that whole thing would be the pressure of the oxygen and plus the pressure of the nitrogen plus the pressure of the hydrogen and so forth. So in other words, the total pressure in that balloon would be the pressure of each of the individual gases added together. Next slide. And that's what we see here. So the Dalton's law says that the total pressure is the pressure of each gas added together. This is done at constant temperature, and also the volume has to be the same. So all you have to do is figure out the pressure of each gas, which might be hard, but I don't think that's really so much the point, although this is a very widely used equation here, but we're going to do some other things with it. So let's go to the next slide. So also, this is not to do with Dalton's law. This is just a definition, which you already know, and that is that the mole fraction of something is how many moles do you have. Like, for example, if you have a mixture of water and you put some, let's say, some sugar in it, then if you want to know the mole fraction of the sugar, you divide the number of moles of sugar by the total number of moles of sugar and water. That's all we're saying. We call that the mole fraction of, in that case, the sugar, but it can be for anything. And the way that we write this is like this. We say the mole fraction, and this thing right here is actually not an X, but you can call it X if you want to. It's actually the Greek letter chi. So that's the mole fraction. It's just the number of moles of whatever you're dealing with or you're interested in divided by the total number of moles in the system. Okay, now this has nothing to do with Dalton's law. It's just a definition, but we had to put it in here because what we're going to do is we're going to see that for gases, and I think actually I'm just going to go ahead and, you'll forgive me, I'm going to try to sit down because I'm just dying here. So I'm going to try to sit down. Oh. Okay. Let's set this thing down. Okay. What we're going to do here, and I'm going to go ahead and show you now before I click, is we're going to rewrite this because it turns out that for gases only, so this won't work for solids or liquids for obvious reasons, but it turns out that because of PV equals nRT, which I'm not going to write the whole thing out, PV and equal signs are hard to make. PV equals nRT, the N in that equation, I'm going to write that, and I'm going to stop, but there would be an RT on the other side, right? If we rearranged that, we would have N equals PV equals R over RT for both this thing on the top and this thing on the bottom. But if everything else except for the pressure is constant, then we could also, only for gases, we could also write this a different way. And I'm going to go ahead and do it now for emphasis. Would just be the pressure, and this is going to look weird, the pressure of the gas you're interested in over the total pressure. And that is kind of like a derivative of Dalton's law. It's the total pressure divided into the pressure of whatever you're interested in. So notice we can write the mole fraction here the way we always have in the past, where it's just the number of moles, how much you have over how much one mole weighs. In this case, though, it would be the number, that would be the N on top, but the mole fraction would be the number of moles of whatever you're interested in divided by the total number of moles. But for gases only, you can also write it that the mole fraction, so again, this is also a different way that you can write the mole fraction. And this is, again, this is the Greek letter chi, the mole fraction of something I, some element I in the gas, would be its pressure divided by the total pressure. So that's weird, right? I mean, it doesn't seem logical that it would work that way, but it does. And there's a derivation on the next slide, which I'm not going to go through for the sake of time, but you should look at it just to get an idea of where this comes from. But what this means is that since it would be extremely hard, like let's say we go back to our example I mentioned a moment ago where you have 4 different gases in a balloon, it would be extremely hard to figure out how many moles of each gas you had and then total them. But it isn't particularly difficult to measure the pressure of each gas and the total pressure. And so because you can do that easily, or relatively easily, then it's very straightforward just to use this formula right here to figure out how many moles of each gas you have by just dividing the pressure of each gas in turn by the total pressure. Let's go to the next slide. So this is the derivation, which you can pause and look at if you want to. Down here we see here that so what we just said on the previous slide is right here. The mole fraction of some gas, which we're referring to here is 1, gas 1. The mole fraction of that would be its pressure divided by the total pressure. So for example, if its pressure was a half an atmosphere and the total pressure was 1 atmosphere, then its mole fraction would be 0.5. And you don't have to count the individual atoms or molecules of the gas. Now, we can also rearrange this equation as we've done down here by multiplying both sides by the total pressure. And if you did that, you'd have P1 equals chi1, or the mole fraction 1, times the total pressure, which is written at the bottom here. So this is just a different way of writing this. And when you use it this way, what you can do is you can take the mole fraction of that gas, multiply it by the total pressure, and you'll get the pressure of that gas. So it's basically just a different way of looking at, get that to right there. It's just a different way of looking at this thing up here. It's just rearranged. Okay, so you can do different various interesting problems with this. Let's go to the next slide. And here's an example. Consider the following apparatus containing helium in both sides at 45 degrees centigrade. And we're going to consider that this temperature is going to be constant. After the valve is open, what is the pressure of the helium? So we have helium on this side and we have helium on this side. So what we can do here is we can use P1V1 equals P2V2 for this side, and then use P1V1 equals P2V2 for this side and figure out what the pressure is for both of them, and then add them together, and that will give us our answer. So on the left here, P1V1 is going to be 18. 2 times 9 is 18. And then V2 is when we open the valve here. So the V2 is going to be 9 plus 3, which is 12. So again, 18 divided by 12 is going to be 1.5, which is what you would end up for your P2, 1.5 atmospheres. And then we can do the same thing over here. So P1V1 is going to be 3 times 3 is 9. And then we would divide that by the new volume, which is 12 liters. 9 liters on the left, 3 liters on the right is 12. And that's 3/4, which we would then have for the the V2 for the helium that was originally on this side. So this value here is for the helium that was originally on the left, and then we would have 0.75 for what was originally on the right. And when we add these together, we get the total pressure. Oh, that is not liters, that's atmospheres, which I'm just going to write as an A, and 0.75 atmospheres for the helium that was originally on the right. Okay, so we would just add those together because the pressure would be the total. So what do you get when you add 1.5 to 0.75? You get 2.25 atmospheres. So let's go to the next slide. And that's what we actually do get down here at the bottom. Now it mentions here that there's another way that you can do this if you want to, and I did not include that in these slides, but it is in your other slides that are on Canvas. So if you want to look at the alternative method, you can. So I would know how to do this problem for the test. Next slide. All right, so we're going to have to go through this like really fast. So kinetic molecular theory of gases involves a lot of stuff that you really study hard when you get to grad school in chemistry. We're not going to really worry about it that much here, but let's just go ahead to the next slide and look at some assumptions. So for gases, the kinetic molecular theory, and you could see this on the final as a multiple choice question, says the following thing. There's 5 things listed here. A gas consists of, so I'm just going to read them real quickly, and you can pause this if you want to. A gas consists of tiny particles, atoms or molecules moving about at random. 2, the volume is negligible compared with the total volume of the gas. So most of the volume of a gas is what? Empty space. 3, the gas particles act independently. There are no attractive or repulsive forces. Now, we know that 2 and 3 are not true, strictly speaking, right? Because they do have a volume and they do have either attraction or repulsive forces. So what we're basically talking about here is something that doesn't really happen exactly like this, but as long as your volume is fairly large and your temperature is fairly low, pressure is fairly low, temperature is fairly high, then you kind of have this. Next slide. And then also they're considering that whenever these gas particles bump into each other, which they do many, many, many times per second, that all the energy is retained by the particles. They don't lose any, but again, that's not true either. Because when they bump into each other, they're going to lose some of their momentum. But we're going to consider that they don't. And then also the average kinetic energy here, number 5, is proportional to its temperature. So that number 5 thing, I mean, you don't really need to focus in on it too much right now, but in 1412 we'll come back to that. Next slide. All right, so here's a little concept check that you can do, and we're literally out of time right now, and we still have over 30 slides to get through, so I'm going to skip these. So I'm going to skip like the next 3 or 4 slides, and I recommend that you do these just while you're watching the video, just pause it. So next slide, next slide, next slide, next, 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 and next, and next, next. Okay, and let's stop here. So that got us kind of, we still have 25 slides to go, good grief. So I've got to hurry. So you have a sample of nitrogen gas in a container. I'm just going to go ahead and read this, and then I'm going to tell you how to do the problems that they're going to give us in the next few slides. And then I'll let you go through them at your leisure on the YouTube video. So let me just explain this. We start off with nitrogen gas in this container. This actually is a cylinder with a piston. And we're starting off with 6 atmospheres, and it's going to stay at 6 atmospheres. And we start off at a temperature of 45 degrees centigrade. And we're going to let this one change. And the volume also will let it change, and it starts off at 6 liters. So what they're saying for this first part is, if you keep the pressure constant and drop the temperature, what's going to happen to this volume? And the answer is, and I'll let you look at it on your own, is that it is going to decrease. Because when you decrease the temperature, you're going to decrease the volume. Okay, so the first part they're going to ask you is what would happen, and the answer is the volume is going to decrease. So they give you like 5 answer choices. I think that's on the next slide. So you're going to just choose the volume would decrease. Of course, you want to understand why. And then they're going to tell you that it's actually going to decrease to a certain temperature, and they want you to figure out what the volume would be. And so what you're going to want to do is use a shortcut because it's a before after scenario. So the pressure is going to be constant here. The temperature's changing and the volume's changing, and that one goes V1 over T1 equals V2 over T2. So if you want, you can use the shortcut there. I mean, really, for all of the shortcuts, if you wanted to do it, you could use the ideal gas law on both sides, but it's just a waste of time. So I would use V1 over T1 equals V2 over T2, where your V1 is going to be 6 liters, your T1 is going to be whatever you get when you add 273 to 45. And then when you cool it, they give you the temperature after you cool it, and I think it drops to 15. So your T2 would be 273 plus 15, if I'm remembering this correctly, which would be 288. And so the only thing that you don't know is V2, right? But you can use the V1 over T1 equals V2 over T2 to find that. So let's go to the next slide. And the answer is going to be D here. The volume the volume decreases. Next slide. Next slide. Next slide. So they do cool it to 15 degrees centigrade, so that would be 288. I'm not going to write it because it'll take too long. So this is going to go to 288 Kelvin, so that would be your T2, and you just solve for V2 using V1 over T1 equals V2 over T2. Let's go to the next slide. Okay, and when you use V1 over T1 equals V2 over T2, you have everything except V2, and so you solve for that, and you get 5.43 liters. Let's go to the next slide. Oh, gosh. Okay, so the kinetic molecular theory of gas. Next slide. The take-home thing that you need to remember from this slide is this part right here that I'm circling. Now, this, again, is the kind of thing that if you go to grad school in chemistry, you get this out the nose. In this particular case, what we care about is this part right here that I'm underlining and this part right here. So we're talking about gases again here. This whole chapter is about gases. And what they're saying here, this V is not volume, this is velocity. So watch that. This is lowercase. Lowercase v is velocity. And the thing that we care about is that m, where the m is the mass of either the atom or the molecule that the gas is made of, right? So what are we seeing here? This relationship is that as the mass gets bigger, the velocity goes down, and that's just common sense. The bigger it is, the slower it's going to go. That's what they're telling us. So you might think to yourself, okay, then if I make it twice as heavy, it should go half as fast. Well, not exactly, but you're on the right track. But it actually wouldn't go that way. It would actually go by the square root of the mass. So if you made it 4 times as massive, it would go twice as slow. So in other words, if you increase the mass by a power of 4, then it would slow down in velocity by a power of the square root of 4, which is 2. So if you'll notice here, this 1/2, if you didn't already know this, if you raise something to the 1/2 power, it's the same thing as taking the square root. So the velocity will go indirectly proportional to the mass. In other words, as it says here, the heavier the particle, the slower it will go, and it goes by the square root. So let's just say if you increased the mass by a factor of 9, how much would it slow down? Well, it would slow down by the square root of 9, which would be what? 3. Let's go to the next slide. Okay, so we're going to come back to this. This is something that, I think I saw this on a final exam once in 1311, so you might just kind of like look at this, but the most important part of this is this. Notice here they didn't write it where it's to the 1/2 power. They actually wrote out the radical here. It's the same thing. So the important part here is that, and this is actually velocity, it's just a different way of writing velocity. Also, you might want to notice here also, I didn't talk about this before, but what happens if you increase the temperature? Well, also it increases the velocity, and again, it's by the square root. So if you increase the absolute temperature by a factor of 4, then it would go up to twice the velocity. Okay, so, this is the kind of thing you might rarely see on a final exam. This thing right here, I'm not going to ask you on my exams. Next slide. Okay, so what are some of these velocities? All of these things, by the way, are averages. So that doesn't mean that every helium atom at a certain temperature goes this fast. It means that the average would be 1360 for helium. H2, it would be 1960. Water would be 650. Notice, so what's happening? Well, this weighs 2, this one weighs 2, this one's 4. So we expect it to slow down by a factor of square root of 2. This one weighs 18. So that's about 16, so it should slow down by a factor of 4. The square root of 16 is 4. But it wouldn't be 16, it would be 16, it would be 18 divided by 4 here, so it would be about 4, so it should go by a factor of 2, and that's about what is happening here. Anyway, you don't have to worry about that. So anyway, what's happening here, if you look here, these masses at the bottom are getting bigger as we go this way, and the velocities are getting slower and slower, right? That's what we care about. Next slide. Next slide. So as I said here, that each one of those values we saw on that other slide is going to be actually something that actually looks like this, where they're just taking the mean velocity. So, and that doesn't necessarily mean that the mean velocity would be right there at the top. It probably actually would be a little bit to the right of the top, because we've got more stuff on this side than we do on this side because of the way it's shaped. But I mean, you don't need to know that. So this is what we call a root mean squared distribution. So at a given temperature, like for example, the first one here is at 200 Kelvin, every one of those things we looked at before, the H2 and the HE, etc., would all have their own characteristic curve that would look like this, from which you could figure out a mean velocity, which is what we were looking at before. Next slide. Graham's law, let's go on to the next slide. So here you'll need to remember this. Whenever you have a gas on one side of a container with a pinhole and you open it so that the gas can start to come out into the empty chamber, then that is called effusion. You'll need to remember that because there's something else called diffusion, which is a little bit different, which we'll look at in just a minute. But when you have effusion, the one that we have right here, there's nothing over here on this side to slow any of the stuff that's coming out of this pinhole down. So there's going to be a law that will govern how fast the rate of effusion will be. And it's the same thing we saw before. It's proportional. Remember a few slides back we were saying that it's inversely proportional to the mass, but it's not the mass, it's the square root of the mass, right? So this mass right here is standing for mass, this M stands for mass. So we have the same relationship. The rate of effusion is proportional, or actually it's inversely proportional, or you could say it's proportional to 1 over the square root of the mass. So this is the same thing we saw before, which is why I emphasized it. If you have two gases and they're both effusing, the rate of the, let's say the top one here, let's say for A here that I'm pointing at, would be inversely proportional to the square root of its mass, and the rate of B, which they've written under A, would be inversely proportional to the square root of its mass. But so if you write them the way that they've written them here, you can see that it's just like if you flip A and B, where the rates are on the left-hand side, A over B, and they're proportional to the masses, which are written on the right-hand side. But again, it's not actually the mass, it's the square root of the mass. And so what you might see in a problem would be that they could give you, like you've got 4 different things here, right? You've got 2 on the left and 2 on the right. So what they could do on a problem would be to give you 3 of those 4 and ask you to figure out the 4th one. But some of the problems that I've seen, they don't make it quite as obvious what they're asking. So if we get a problem like that, which I think we do have one in the work problems, then we'll talk about it more then. Let's go to the next slide. Let's say the difference between effusion and diffusion is that diffusion, you don't just have one gas on one side going to the other side. You have a gas on this side also going to this side. So they're getting in each other's way. They're bumping into each other. So you can't use Graham's law of effusion for diffusion. You can, but it isn't as accurate. Next slide. So again, here is Graham's law of diffusion. So this is the way you would see this on a problem. They might give you the two masses and ask you to figure out what the rate ratios would be. Like, for example, if they gave you M2 is 9 and M1 is 4, take the square root of 9, that's 3, the square root of 4 is 2. So the ratio would be 3 to 2, which means that the rate for gas 1 compared to the rate of gas 2 would be 3 to 2. So if the rate of gas 2 is 4, then the rate of gas 1, if you were asked to figure that out, would have to be 6. Next slide. Next slide. All right, I only put this slide in here because they may ask this one also on the final. This is called the root mean path, and it's the mean free path. And what that means is just it's how far either a gas atom or a gas molecule would travel before it hits another one, which isn't very far, believe me. So whatever that distance is, the average distance here for all of these things would be the root, sorry, I keep saying that, the mean free path. Okay, I'm getting this mixed up with root mean square. The mean free path. So again, you could see this on the final. They do sometimes ask this as a multiple choice where they'll just ask you what it means. No pun intended. So if they ask you what is meant by the mean free path, it's the distance that this gas molecule or atom travels before it bumps into something else. Next slide. The behavior of real gases is like the ideal gas law, kind of. Some gases don't behave very much like that, but a lot of them do. But we have to put in two factors, and so for the sake of time, I'm just going to explain this to you, and then I'm just going to flip through the slides real quickly. The only things we have to change out of PV and RT is the P and the V. The reason is because the pressure of a real gas is going to be lower than the pressure of an ideal gas because there are attractive forces. So whenever they bump into each other, they kind of hold on to each other. That causes the pressure of the gas to go down. So you have to add in a factor to get it to the point where it would be if it were an ideal gas. So what we're trying to do here is we're trying to convert real gases behavior into ideal gases behavior by doing some modifications to the ideal gas law. And you will almost always see a problem on the test, on the final, where they'll ask you, somehow or other they'll ask you, what does the, well, I have to give you the name of this equation we're going to get ready to derive in order to ask this question. So I'm going to wait for just a minute before I do that. So let's hold off on that. I'll just say this, that you'll almost always see a problem from this section on the final. And I'll talk about it more in just a second. So for the pressure, we have to add in a factor that's called the A factor, and it's actually multiplied by a couple of other things. But well, the main thing is that we have to add a little lowercase a factor to it to get it right. And then for the volume of a real gas is actually, I mean, like if you just were looking at the volume of the particles, would be larger than it would be for an ideal gas, because for an ideal gas, we're assuming there's no volume. So for the volume, we have to subtract another factor, which we call the B factor, and it's actually the B factor, which you would look up in a chart, and that's multiplied by how many moles you have of the gas. So it turns out to be, instead of PV equals nRT, it's just P plus the A factor multiplied by some things that have to do with N and V, and then that would be multiplied by not V, but V minus NB, or V minus BN, where N is the number of moles and B is the factor, equals nRT. Next slide. Let's go to the next slide. I'll let you pause and look at that if you want. So for the pressure, we have to add in this factor right here, where this thing A is what I was talking about before, where you would actually have to look this thing up in a chart, and there's a different A value for different kinds of gases. So you multiply the A times the number of moles squared divided by the volume squared, and then you would add whatever you get when you do this to the pressure that you have. So this would be the actual pressure that you're measuring. Next slide. So for the volume, you have to subtract. So notice here, just very briefly, these little atoms or whatever they are, they actually do have a volume, right? So they're not zero like we assume for ideal gases. So if we want to try to convert this so that we can use it in the ideal gas law, we have to subtract something away to get those to zero. So there's another factor called the B factor right here. And you multiply that, you look it up in the chart, and then you multiply it by the number of moles of gas and subtract that from the volume. And that's, again, the measured volume. And then everything else remains the same. PV equals nRT. Next slide. Next slide. Next slide. So you end up with this right here. And this is called, and this is why I couldn't say it a minute ago, this is called the van der Waals equation. And this is for real gases. So as I was saying before, you'll almost always have a problem on the final or a question asking you what the equation is that relates real gases to ideal gases. And it's called the van der Waals equation, but they may also ask it like, you know, like, I mean, in an extreme case, they could actually give you N and V and then give you either a chart to look up A or look up B, or they can just tell you what they are. And then they could actually ask you to figure this out. I don't know if I've ever actually seen that. I think I may have seen it one time, but that was years ago. So, but still, you should be familiar with this. So this is called the van der Waals equation, and its use is to convert real gases into a form for ideal gases. In other words, it's so that you can actually use the ideal gas law in this kind of a varied form here for real gases. Next slide. Here is a list of the A factors, and here are the B factors. For example, for helium, A is 0.0341, and for helium, B is 0.0237, and they're given in the appropriate unit so that when you multiply through, you wind up with liters for the B thing and atmospheres for the A thing. Next slide. Okay, so we definitely need to cut this short. So hopefully you'll understand this stuff a little better now. And of course, if you don't get it now, just you may want to go back through it again. And then also when we do the work problems for Chapter 10, maybe that will also help to clarify some of the things that you didn't get. Let's stop now. So I'll see you in the work problems.